Hey data junkies, welcome back to INST 314, Statistics for Information Science. I'm your host, Shawn Janzen. Now, we're moving on with our talk on the chi-squares, and our previous videos were looking at the goodness of fit. We're now moving into the other half of the chi-square family, the test for independence. And this topic 6.1 is going to be starting with the foundations of it. We're going to start with a recap of the chi-square basics and the goodness of fit, comparing it to see how it differentiates from the goodness of fit as we move into the test for independence. Future videos are going to be looking at to see how we actually calculate the test for independence, and we're going to have the walkthrough videos in Excel and R. The last video is going to wrap up with effect sizes and power testing. So let's get started with the foundations. The chi-square test for independence, we said before, uses two variables, and this is used to see if these two variables are independent from each other. Do they have a relationship with each other or not? Does one variable's distribution make a difference based on the distribution of a second variable? Contrast this with the goodness of fit, where the goodness of fit was only one variable. And in the goodness of fit, we were trying to see of that one variable's distribution, did those frequencies that we observe differ from those we would expect to find of a population, right? So the measures of the same variable at the population. We're still concerned about populations with the test of independence, but we're not talking about the distribution of one variable, okay? And that's the key distinction between the goodness of fit and the test for independence. When we're talking about the chi-square test of independence hypothesis testing, we then say that in the null, that they are independent. What happens with one has no bearing on what happens with the other. Whereas with the alternative, we say that they are dependent. There is a relationship, they are associated, that what happens with one variable does affect the distribution of the other one, and we see it as it distributes across the frequencies observed in our bivariate tables. So making bivariate tables, I just mentioned that we're going to see that these distributions are going to change over bivariate tables. And in our earlier modules on descriptive statistics, we started working on making bivariate tables. So in this case, when you're doing the chi-square, it doesn't really matter so much if our independent variable goes in the rows or in the columns. The chi-square is going to figure out the math, and it's going to be the same either way. But it's useful for us to keep track of which one it's in. We're going to need that later when we start talking about effect sizes and things like that. Now, keep in mind, when we make these bivariate tables, we're going to have one column for every category of the IV, and one row for every category of the DV, or vice versa, depending on which one you put in the rows and columns. But in general, one category for every column and row. Now, the size of your bivariate table is going to be based on the number of cells in the table, and that size is going to be based on the product of the rows and the columns. So they get multiplied together, such that if you had a categorical IV with 2 categories and a DV with 5 categories, we would produce a 5 by 2 table that is going to have 10 cells, 5 times 2. Looking at the math that goes into the chi-square, as we compare the goodness of fit and the test for independence, it has the exact same formula. Fantastic, less you have to cover. But they do have a little bit differences beyond the formula itself. In the goodness of fit, we only have 1 degree of freedom, where k is the number of groups, and it's k minus 1 for your degrees of freedom. In the test for independence, it's a little bit different. In this case, it's still a k minus 1, but we have k's for both the IV and the DV. So in this case, what we're looking at is we do a k minus 1 minus a k minus 1, which translates to the number of rows minus 1 times the number of columns minus 1. And so also then, what is the same is the citation. If you can do the APA citation for goodness of fit, it's the exact same for a test for independence. Now, there are some weaknesses and limitations to the chi-square itself, and this is going to apply to the goodness of fit as well as the test for independence, but it becomes much more salient in the test for independence because, like all hypothesis testing, the chi-square is sensitive to its sample size. And when you're dealing with bivariate tables, the more cells you have in your bivariate table, the larger your chi-square statistic can be. We're looking at taking the differences between the frequencies observed and the frequencies expected. So the more cells that you have in a table, the more opportunities we have to find differences between frequencies observed and frequencies expected, and they sum across the table. It becomes a sort of snowballing effect. So even small differences can continually sum up into a larger number as we get across the way. Degrees of freedom control for this a little bit. As degrees of freedom increase, the critical values adjust accordingly, but it doesn't take care of it completely. So the larger your table, the more likely you might be able to find a large chi-square value. Also keep in mind that with large samples, even these trivial relationships can become significant. And statistical significance is not the same as importance, which you may hear me call substantive significance. If we're doing this in R, and there's a chance that we might get the warning message that's on the screen at the moment that says, in CHISQ.test object, the chi-square approximation may be incorrect. This is just a warning, it's not an error. Your chi-square did work. However, it might not be accurate, at least according to what we need. This is a chance for R to tell us that we might have a breakdown in our chi-square analysis, that the results might be inaccurate. If you were to do this by hand, or you're doing this in Excel, which we could consider by hand, then you could have the exact same results, but you're not going to get this error message and this error warning. Sorry, not an error, just a warning. So let's figure out why this happens to be. Well, the reason it usually happens is that this is a soft rule here, not a hard and fast rule, that when about 20% of the cells that you have, 1/5 of them, have frequencies that are less than 5. 5 is also relative to the sample size. So if you're dealing with data that's in the thousands or the millions, getting 5 is going to be easy. So that number 5 might be a bit larger. It's going to be relative to the other sizes of n's in the different cells on the table. Now, when you have that small value, it's going to mess with the chi-square test itself and cause this approximation warning to come up. So what do we do about it? Well, you have 3 possible strategies. You could ignore it. You could just leave it alone and move on. If you do this option, you must tell your reader about it when you do the write-up, especially if you're in the workplace or you're writing for some publication or whatnot, and you want to be able to tell your readers that here's the number might not be right. And if they're a decision maker, then it goes on them to be able to say, are we going to trust the numbers that you've put out through your analysis or not? The other options you could do is you could drop the offending rows and columns. Wherever that cell is located in the bivariate table, get rid of it. Now, a pro to this side is that you've gotten rid of the cells that have the small sample sizes, and so hopefully your chi-square approximation warning will be gone. But the downside is that not only have you gotten rid of that cell, but you have probably also gotten rid of other cells in the table, because you will either get rid of the entire row or column that it's in. Additionally, you're getting rid of some of your sample size overall, which could have effects when you're talking about, are you creating missing values now and having problems with representativeness? Is your sample size too small now? And things like that. Another option is recode it. Take that cell and merge it with other cells in the table. This means recoding by the rows or the columns of the variables. And so the pro here is that you're not losing your sample size and you're not creating missing values, but the con is that you are muddying up your categories a little bit. When you recode them to combine groups, those groups aren't giving you as much granular level information as it might have before. And how much granularity you're losing is really going to be dependent upon the context of which variables it is that you're looking at. And again, just to recap, you only get this warning in R, not in Excel. So keep that in mind that if you are working in Excel, you have to be a little more cognizant about the distributions of your tables and where you might be at. So lastly, I want to leave you with just some of the chi-square test assumptions and let you know they're the same as the goodness of fit. We have to assume that they're independent, so observations are not going to be influencing each other in your data, and the sample size, we want to have at least 5 in our cell count, otherwise we can get the approximation warning. And with that, I'll see you all in the next video.